Hello everyone, here's another Physics IB past paper review. This one is May 2018, standard level paper 1, and this is page 11, which has question 20 and 21. Let's take a quick peek at question 20. It's to do with Kirchhoff's laws and power dissipation. So we're going to need our data sheet, here it is, and of course here's our Kirchhoff's laws, loop law and junction law, and then this is going to be our power dissipation in here. Okay, so the question is giving us 5 resistors of equal resistance connected as shown in the diagram. So because all the resistors are the same, let's first of all think about which power dissipation law we want to use. Now, the resistors are going to be the same, so that's a constant. So if we look at what we have here, we're going to be analyzing the power dissipation. This I squared R is going to give us, because we're going to do Kirchhoff's laws to work out the current moving through each of these resistors. That's going to be a variable that we need to figure out. And once that we've figured out that variable, if we multiply it by this constant, then we should get the power dissipation. So I'm going to suggest that we go ahead and use this part of our power dissipation. In other words, the power dissipation is just going to be proportional to the current squared. We can ignore the R bit because we're going to assume that's the same, other than the fact that we can see that in this part of the loop, the constant is going to be multiplied by 2. So whatever that value is. Okay, but most of this is going to be to do with Kirchhoff's laws. So let's recap. This might take a little while, so it's a good opportunity to get our heads around how to do this. Let's start with our voltage law. So we're going to say that the voltage law in a loop is equal to IR. Okay, so what does that mean? Well, let's go ahead and state what we mean. We're going to have a voltage here. So there's a voltage, and we're going to call this our EMF right here. And I'm going to say that it's a positive value when it's going this way. Okay, so I'm just going to go with conventional current. I'm going to pick my loop. It's going to go all the way through the top and through this top, all the way around and back to here. And this is going to be a positive. So I'm going to make my statement here. Let's go ahead and make statement number 1 down the bottom. I'm going to say whatever this EMF value is, the voltage supplied, that's going to be equal to the current. I'm going to say current 1 multiplied by the resistance. So obviously we need to expand on that a little bit. So let's keep going. We're going to say, let's say that this is current 1. And then up here is current 2. This would be current 3. This here would be current 4. And this is going to be current 5. And they're all going to be different. Well, actually, 2 and 3 will be the same because the resistance X and the one below it are going to be the same resistance. So they'll be the same, but we need to think about them all separately. So if I follow this red route through, I can say that I1 is the same as I2 and I4. So I'm going to split that up. So the EMF, the voltage, is going to be equal to I2 plus I4. Now, to bring the resistance into play, I'm going to go ahead and say that my resistance for all of these, I'm going to state it at the top. I'm just going to say, I'm going to say that my resistance is going to just be 1 for each of these resistors. So I'm just picking a ratio value. Now, as it goes through this loop, you can see that there's just one resistor. So I'm just going to say that that's 1. I2, in other words, my R is just 1. But as it goes through this part, you can see that there's 2 of these resistors. So I need to state that this is actually going to be 2 I4. Okay, so let's keep going with our voltage loops. Now this red loop had an EMF in there, it had a voltage, but my next loop is not going to have a voltage because my next loop is just going to be in here, and I'm going to say that it's going this direction. So when I'm referring to my current 2, my I2, that's going to be positive because it's the same way as my positive red loop. And when I'm referring to my I3, that's going to be negative. So what's the voltage in this loop? Well, the voltage in this loop is 0. There's no EMF. And I'm going to say I then have one resistor in my I2. So that's 1I2 plus my negative. So I'm just going to go ahead and say negative 1 resistor in my I3. Okay, so nice and simple. I2 equals I3 because the resistors are the same. All right, next one is the loop with the 3 resistors in it. So I'm going to keep my loops going the same way, this way, which means when I'm referring to my current 4, my I4, that's going to be positive, and when I'm referring to my current 5, my I5, it's going to be negative. This one, we have to deal with the 2 resistors in the top, the top row. So, is there any voltage? No, it's just a straightforward resistor loop. And my positive now is the I4, so it's going to be a positive I4. And remember, this time I've got 2 resistors in there. So there's 2 resistors in my I4, minus, because I'm going backwards now, I'm going against the current, so I'm giving it a minus annotation, and that's just going to be the 1, and that's I5. So if we take a look at what that means, it means that I5 is equal to 2 I4s. And that makes qualitative sense, doesn't it? Because if we use our analogy of the water flowing through pipes, if there's 2 different possible pipes for it to flow through, one of the pipes has twice as much resistance, in other words, it's twice as small, then you're going to get more current flowing through the pipe that is bigger, the pipe that has less resistance. And since it's a factor of 2, you'd expect there to be twice as much water flowing through the twice as big pipe. Okay, so we've dealt with our voltage loop stuff. Now we're going to take a peek at our current loops. So remember, this is to do with junctions. So where are the junctions? Well, there's a junction here, and there's a junction here. Okay, so I'm going to say that the total current, the I1, which is the current flowing through the whole system, is going to be equal to, so this is a junction coming in, this is my junction coming in, this is going to be equal to the junctions coming out. Okay, so I1 is equal to I2 plus I3. Okay, and this is going to be the same or equal to these 2 junctions. So I can just extend that, I can just keep going. I can say that's equal to I4 plus I5. So I've now got everything I need to solve, and I'm going to start focusing, just with these ratios, I'm going to start focusing on the power dissipation. There's power is equal to I squared times R. Now let's deal, we're trying to figure out which one is the greatest power dissipator. And hopefully you can see, because we're going to be dealing with different currents, it's not going to be D. It's either A, B, or C. The question is which one. And to figure out which one has the greatest power, we're interested in which one has the greatest current flowing through it. So we're going to be comparing. I'm going to compare X to Y and Y to Z, and really just comparing all 3 of these and to see which one has the greatest current. So you can see already when we're comparing 5 and 4, okay, this is going to tell us which one's greater, whether it's Y or Z. Well, take a look. I5 is equal to 2 of I4s. Okay, so that means 5 is going to have a greater current, which means when you multiply that by itself, or you square it, when you square it, it's going to give you a bigger power dissipation. But we also have to multiply it by R, and when we're talking about I4, in other words, resistor Y, we need to multiply that by 2. So we need to deal with this first. Which one's going to have the bigger power dissipation? Is it going to be resistor Z in current 5, or is it going to be resistor Y in current 4? So let's put these ratios in. So let's bring our power dissipation value formula down here. So we're going to say power dissipation is this I squared times R. So the power dissipation of, the current in I5 is twice as much as it is in I4. So we're going to put this value in. It's going to be twice as much. Now remember, that's going to be squared. But there's only one resistor in I5. So there it is. Okay. Whereas when we do this, so this would be for Z. When we do it for the power dissipation for Y, we have I, which is the current. Well, that's just going to be, let's just call that 1. So 1 squared. But we need to add the 2 resistors, so 2. Okay, so just using these ratios, hopefully it's pretty clear that we're going to have 2 squared, which clearly is going to be 4 plus 1 is going to be 5 ratio. Whereas over here we have a 3 ratio. So it's a 5-to-3 ratio in favor of resistor Z. So which one creates the greatest power output or the power dissipation? It's gonna be Z beating Y. So at this point we can say that we eliminate Y. Okay, now we just got to take a look at X and Z. Will X beat Z? And so to do that, we're going to take a look at our current junction law here. Okay, let's combine these actually. We're going to say I2 is equal to I3, so we can substitute that in and basically say that 2I2 is equal to I4 plus I5, right? And then remember, we're trying to compare X to Z, because we've eliminated Y. Y is less than, in terms of power, Y is going to be less than Z. And just recall that we'd said when we were comparing the power of Z to the power dissipation of Y, it was a 5-to-3 ratio. Okay, remember we did that before? So let's go ahead and compare, the power dissipation of Z to the power dissipation of X. So we need to consider I5. Okay, so we need to consider I5. We want to substitute that in over here. So we need a statement about I4 to substitute in. So we can take this statement here and substitute in. What can we say about I4? Well, I4 is equal to half of I5, right? That's really what we've said here. So let's substitute that in. So rather than having an I4, I'm going to say 0.5 I5 plus I5. Okay, so let's simplify that a little bit more. We're going to go 2I2 is equal to 1.5 I5s. And then, of course, I2 is going to be 0.75 I5s. Okay, let's put that into our power dissipation formula. So power dissipation for in current 2, which would be the power dissipation of resistor X, that's going to be equal to the current, which is going to be, in this case, just 1. So 1 squared, and then multiplied by the number of resistors, which is going to be 1. So it's just 1. And then the power dissipation for resistor Z, which is I5, is going to be, well, in this case, 0.75 squared plus, well, just the 1 resistor again. Okay, so the ratio here is going to be 1 to, let's make some space. It's going to be a 1 to a 0.75 squared, which is a weird number. It's 0.5 5625. 5625. In other words, what we're saying is that the power dissipation of resistor X is greater, but not much greater than the power dissipation of Z. And so what we can see here is that Z beats X, which means we can eliminate X. And that means that just looking at these ratios here, the winner must be Z. Z must produce the biggest power dissipation of these three resistors. Now that's a long process. Another fun thing to do, rather than using ratios, you could just make up some numbers, and it might be fun just to figure out the actual numbers. If you make up a voltage for the EMF, you could say that this is maybe 60 volts, and then just make up a resistance for each of these. Maybe you call those 5 ohms each. Plug it in, do exactly the same thing, but now you've got some actual numbers to play with, and you'll end up getting basically you'll end up with a power dissipation of Z being the greatest, with X being the second greatest, and then Y being the smallest. Okay, so for question 21, once again we're going to need our data sheet information here, so I'm just going to put it just to the side. We have two resistors in series, X and Y. They're made of uniform cylinders, same material, connected in series. They have equal length. The only difference is that Y has twice the diameter of X. Okay, so just qualitatively speaking, we can look at this and say, well, you can tell that X is going to have an increased resistance compared to Y, because if we use the analogy of pipes, of course, a thinner pipe, not as much water can flow through it, and therefore there's going to be some resistance to that water moving through. So we're going to just qualitatively say that the resistance of X is going to be greater than the resistance of Y. Okay, we can just figure that out just by looking at it. This resistance is going to be, this resistance is higher than this resistance. Okay, the point is though to prove it with ratios. So if we know that the resistance of Y is, we're just going to label it R. So this resistance here is just R. What is the resistance of the whole series combination? Okay, well, if we think about resistance in series, we know that, let's do it over here, we know that the total resistance is just going to be a combination of adding all of the resistors together. So in this case, the total resistance is going to be Rx plus Ry. Okay, we're going to get our solution here eventually. So which formula are we interested in? Well, we know something about the dimensions of the resistor. So if we glance over here at our data sheets, hopefully you can see that we know something about the diameter, which would be the surface area. In other words, this surface area here, if we were to fill that in, that surface area there is going to be pi r squared. Okay, so that's the area there. And we know that they're made of the same material. So if they're made of the same material, then the resistivity, so rho of X, is going to be equal to the rho of Y. And so that's starting to lead us towards our resistivity formula down here. And if we rearrange that, we can say that the resistivity, the resistance, using our resistivity formula, the resistance is going to be rho L, so rho, the resistivity of the material, multiplied by the length. Now the lengths of both of these are the same, so we can add that on as another thing. Length X is equal to length Y. So the resistivity times the length divided by the area. Well, the area is pi r squared, and the areas are not the same. So area X is not the same as area Y. Actually, let's put that as a diameter. We'll go diameter because that's what we're given in the information. the diameter of X is not the same as the diameter of the Y. In fact, you need two diameters to get to the diameter of Y. Two diameters of X to get the diameter of Y. Okay. So we're trying to get a ratio value for the resistance. So if we compare the resistance of X to the resistance of Y, what we're trying to find here is this integer, okay? In other words, how many more times is the resistance of X greater than the resistance of Y? So if we find out the resistance of Y, how many times do we have to multiply it by to get the resistance of X? And so we're going to put our equation into ratio form, because of course all we would need to do here is go Rx over Ry, and that's going to give us this integer multiple ratio. Okay, so we're going to bring this guy over, because this now is the resistance taken into account the differences in the radius and the fact that the resistivities are the same and the lengths are the same. And we're just going to put it into a ratio. So we're going to go rho. So Rx is going to be rho x, which is the same as rho y, multiplied by the length x, divided by pi Rx squared. Just going to put that like that. And then I'm going to divide by, of course, the same, but with regards to y. So rho y, Ly over pi Ry squared. Okay, now this is the fun part, because the resistivities are the same, so they can cancel out. The lengths are the same, so they can cancel out. Of course, pi is the same, so they can cancel out. And that means that our n value, our n ratio that we're trying to find, the multiple of the ratios of the resistance of X to Y, is going to be, well, we're going to bring the radius of Y up to the top, and that's a ratio factor of 2, right? Because the diameter is twice, which means the radius is going to be twice. So 2R squared over R squared. Well, what's that going to be? Well, 2 squared is just 4, and 1 squared is 1. So this is a factor of 4. Okay, and this is an important number. This is the ratio factor here of the resistance of X over the resistance of Y. Okay, so that tells us that resistance X is 4 times the resistance of Y. So now what we can do is plug this into our series ratio statement. Resistance X is 4 times resistance Y, so I'm just going to go 4, and then resistance Y, well, we're just going to keep that as a 1. So the total resistance is 5. So the answer is D.